So having taken a look at the work that was done by Villars and Pettifor, and having seen that how they came to appreciate the role of interatomic interactions in determination of the crystal structure, it becomes pertinent that we start developing a set of concepts and tools with which we can start quantifying this interatomic interactions. Now, there are different ways in which this can be done. So, for instance, people use this density functional theory type of calculations. So these density functional theory calculations are actually pretty sophisticated and high fidelity, but at the same time, they also require good amount of computing resources and require good amount of time, especially if you are going to look at some structures which are fairly complicated. In addition to DFT type of calculation, people also use molecular dynamics. So molecular dynamics, again, that is going to be a time consuming process. So the fast approach to this is to start working with basic thermodynamics. So when I say basic thermodynamics, there are a bunch of models like medium mass model, or there are other types of relatively more sophisticated thermodynamic formalisms like the Calfad method, with which one can start calculating the Gibbs free energy. And then when you look at Gibbs free energy, it is consisting of the formation enthalpy and the configurational entropy. So the formation enthalpy is something that medium mass model or something similar can compute, and then one can easily find out the value of configurational entropy, and then you can get to calculating the total energy of the Gibbs free energy. Okay. So if you are going to be calculating the free energies of material, let us first be clear what free energy really is. Classically, what we say is free energy describes the capacity of a system to do work. So translated to the world of materials, what would you think this capacity to do work would mean? It would mean that in this case, it is about moving the atoms around, meaning that you are breaking bonds, you are reforming bonds such that the total energy of the system decreases. So this is something which is very important to remember. In case of thermodynamics, what it says is essentially higher the energy, lower is the stability, and higher is the reactivity. And so therefore, when the work is being done, essentially the idea is you are trying to move the atoms around in such a way that you are breaking bonds, you are reforming the bonds, and through this process, you are trying to move slowly towards lowering the total energy of the system and trying to get to a stable state. So a high free energy leads the system to reconfigure because it wants to lower the energy, and eventually the system tries to move towards a low energy state. Now when we talk about free energy, you can have the Gibbs free energy and you can have the Helmholtz free energy. So let's go ahead and talking about Gibbs free energy. So Gibbs free energy is going to be given by this expression over here. The free energy is H minus Ts, H being your enthalpy of formation, and S is the entropy. And by and large, when we are looking at entropy, we are simply using the configurational entropy. Now there's a few points that you need to note. The first thing is, more negative the enthalpy, the lower is going to be the Gibbs free energy. So if this component has a negative contribution, the Gibbs free energy is going to come down. Similarly, the higher the entropy is, the more negative this number is, and that also results in lowering the Gibbs free energy. So higher is your entropy, lower is the Gibbs free energy. At the same time, when you are going to higher and higher temperatures, because temperature is multiplied by the entropy over here, the entropic contribution becomes much more dominant and it starts stabilizing the material system. So if I look at the very definition of the formation enthalpy, the change in enthalpy over a certain range of temperature is given by the expression over here. It's the integral of Cp dt. All right. And if you look at the change in entropy, that can also be expressed in terms of the specific heat of the material, and it is given as integral of Cp over T dt. Now, It's not enough to say that I can define my Gibbs free energy in terms of enthalpy and entropy. You need to have a way of either calculating these values or finding them. So the next question is, where will you actually find the type of thermodynamic data that we need if we are not going to calculate it? And one of the important sources for thermodynamic data, which is available open access, and I think it's maintained by NIST, is the JANF tables. So you can go look up the JANF tables and you will get the values of formation enthalpy, you will get the values of Gibbs free energy, so on and so forth. So if you are able to get the values of formation enthalpy, let us see what this actually means. And let us try and develop an understanding of enthalpy. So as a first approximation, the enthalpy is given by this term omega XA XP. So XA and XP here are basically the concentrations of A element and B element, and omega is what we call the interaction parameter. So essentially what it means is when you are bringing A and B atoms together, how strongly they are interacting, the measure of that interaction is being given by this term omega. So let us go ahead and consider the cases shown here. So in the first case, you have a distinct block of blue atoms and you have a distinct block of red atoms. In the second case, they seem to be mixing fairly randomly. In the third case, they are again mixing, but you start seeing some sort of a order. So you have a blue followed by a red, followed by a blue, followed by a red in this direction. If you go in the other direction, again you have got blue followed by red, followed by blue, followed by red. If you start going in the diagonal direction, you start seeing the same color of atom all throughout. So there is a certain order which is found over here. The second case is where you have nice randomness or disorder, and then in the first cases where you are not really having an intermixing of atoms. So now go ahead and think about what would be the sign of omega in each case. So here clearly these blue and red atoms, they don't want to stay close to each other. So whatever interaction is there between the red and blue atom, the idea is they try to stay as far as possible. And so what that means is, in this case, if you get the red and blue atoms to try and mix, the overall Gibbs free energy will be increasing. And so what that means is the formation enthalpy would also have to increase. So this is a case where you will have the interaction parameter being greater than 0. Anytime you have the interaction parameter greater than 0, forming an alloy becomes difficult. Now, of course, entropy is going to stabilize the formation of the alloy, but if the value of omega is much greater than 0, then even the entropy cannot get the alloy to form. So in the first case, where you have got clustering of different types of atoms, the interaction parameter is greater than 0. In the second case, it looks like it doesn't really matter whether you are having a red atom next to a blue atom or a red atom next to a red atom. This is where you have got a complete disorder or random type of structure. So if you have a situation where how the atoms sit next to each other doesn't really matter too much, then that means the interaction is going to be extremely weak. And so here the value of omega is going to be close to 0. The third case is where you have got a very properly defined order. And so basically what's happening is the red and the blue atoms are interacting. So if you look at the nearest neighbors, so that is not along the diagonal but along the x-axis or along the y-axis. If you look at the nearest neighbors, you will see that the two nearest neighbors are going to be atoms which are not alike. And so what that tells you is these two atoms, the blue atom and the red atom, they are actually interacting very strongly and they are trying to stay close to each other. So it means that when you are mixing the red and blue together, you are moving to a stable state, you are actually lowering the Gibbs free energy. So what that means is the interaction parameter is quite likely a negative value over here. Now, as we compute the formation enthalpies, it is important to know that which model should we use for calculation of the formation enthalpy. And there are a number of different types of models. The first one and the simplest one is the ideal solution model. So in case of the ideal solution model, the enthalpy of mixing is 0, and so here you don't really have any interaction between the atoms. So omega is 0. And so if you look at the value of delta G mix, that is simply given by the contribution of the entropy of mixing. And so of course for the entropy of mixing, we have this standard expression which you might have come across in thermodynamics textbooks or thermodynamics courses if you have done those courses. So essentially the entropy of mixing is given as minus R times XA log XA plus XB log XB and so on. And of course, since we have got the R over here, we are expressing the entropy in terms of moles per moles. Now, in case of the ideal solution model, the overall free energy is simply going to be the weighted sum of the free energy of individual A and B coupled with the contribution of the entropy. And so if you plot the Gibbs free energy as a function of the composition, you will see that if this was GA and this is GB, this first term over here is simply given by the straight line, and then the delta G mix is really the amount of stabilization that you are getting as a consequence of entropy. So in absence of interatomic interactions, the mixing is going to stabilize the material. That is the effect of entropy. And for the atoms to stay apart, as we saw just now, the interaction parameter must be positive. Now the ideal solution model is just that, it is idealized, and so we move to a somewhat more realistic scenario, and this is the regular solution model. The world is non-ideal, atoms interact, and therefore we must move beyond the ideal solution model. So to understand the regular solution model, let us take the example of a phase diagram. So this is a fairly simple phase diagram, an eutectic phase diagram between A and B. And so here you also note that quite deliberately we have taken the example of a phase diagram which is nearly symmetric. It's not perfectly symmetric, but you can see that this phase diagram is more or less a symmetric type of phase diagram. And so this is a case where this regular solution model works very well. And in case of the regular solution model, the delta H mix is given by omega times XA times XB. So this expression itself is a symmetric expression about the value of XA and XB being 0.5. And so I think now you can start understanding that when we are considering this delta H mix as a very symmetric expression in case of the regular solution model, why it actually makes sense to look at examples where the phase diagrams are fairly symmetric. Because if you look at the other contribution to Gibbs free energy, which comes from entropy, this is also a very symmetric expression about XA equal to XB equal to 0.5. And so you basically have only a very slight asymmetry in G, and this becomes possible because of the asymmetry in the free energy of the individual elements A and B. So this is really what is driving the asymmetry in the Gibbs free energy in case of regular solution model. But then you have got some rather complicated phase diagrams which are not symmetric. So for example, if you look at this copper zinc phase diagram, you will see that there is a tremendous solubility of zinc in copper, but you have got very little solubility of copper in zinc. And therefore, what this would suggest is if you are looking at the interaction where copper is surrounded by zinc and where zinc is surrounded by copper, the nature of interactions are actually going to be vastly different. And that is reflected in this vastly different solid solubilities at the terminal ends. Now there's a couple of things that you can try and do. Just pause the video and try and see if you can explain this type of phase diagram using Hume-Rothery rules. That's the first one. And the second thing is, as we move forward, we need to understand how we can model this type of complicated systems, this type of complicated phase diagrams from a thermodynamic perspective. And that is where we use we introduce our next level of complexity, which comes in form of this subregular solution model. So the subregular solution model is given by this expression. So this part obviously I think you can recognize, that is the configurational entropy. But then if you look at this first part, you will realize that this thing, if you consider this entire thing as omega, you are basically drawing an analogy with the regular solution model, which says delta H mix is omega XA times XB. So here you still have the XA XB, but then this omega has become much more complicated. And so what we are basically saying is you've got two interaction parameters, omega BA, which is the interaction of B atoms with A atoms when B is surrounded by A, meaning you are trying to dissolve B in A. And then you have got omega AB, which is the interaction of A atoms with B atoms when A is surrounded by B, meaning that you are trying to dissolve A in B. So this effective omega is really going to be a composition weighted average of the individual omega AB and omega BA. So now you can see that the moment you have this type of expression, you can build in the asymmetry in the interaction between the atoms. So here the asymmetry is arising as a result of a huge differences in the value of omega AB and omega BA. If the values of omega AB and omega BA are going to be fairly similar, then the subregular solution model is going to give you results which are very similar to the regular solution models. But usually for cases where your phase diagrams and all are not symmetric at all, the values of omega AB and omega BA are going to be quite a bit different. And this becomes quite accentuated at the terminal ends of the composition range. So in a nutshell, this is some of the really basic thermodynamic aspects. So as we go forward, we have to realize that during alloying, not only do you have a chemical contribution to the enthalpy, but you also have the effect of entropy, which starts stabilizing the single phase solid solution chemically disordered structure at high temperatures, especially. In addition to the chemical contribution, you also have to consider that when you are making an alloy, you are bringing different types of atoms together. The size of these atoms would be different, and the size misfit can also result in a little bit of a strain in the lattice, and so that is going to add another positive contribution to the energy, meaning that it is going to raise the energy and it's going to make things a little bit unstable. So this is something that we call as the lattice strain energy. And as we move forward in this course and we start calculating the different thermodynamic features, we will see that it becomes very convenient to calculate the chemical contributions to the enthalpy using Miedema's semi-empirical model. That is simply because of the nature of the model, where the equations are quite simple, no complex equation solving is needed. And similar to Miedema's model, actually in Miedema's framework, he used Eshelby's model to compute the lattice strain energy. Now, just a caveat, the Eshelby's model was actually not derived for an atomistic case. Eshelby was making this model to compute the interaction energies when you are adding an impurity inside a host matrix. So the length scale was different, but nonetheless, given the assumptions of Miedema's model, he was able to make use of Eshelby's model in order to calculate the lattice strain energies. So with Miedema and Eshelby, you can start calculating the thermodynamic features in a number of materials informatics problems that we will take up as we move ahead in this course. Now, this really is the key part as far as thermodynamics is concerned. Your ideas about delta G, delta H and delta S. And since we are looking at largely solution thermodynamics, we will be content with looking at delta G, delta H and delta S. Of course, people who look at other techniques, especially people who do a lot of DFT, instead of delta G, they will actually look at delta F, and since delta F basically is the change in Helmholtz free energy. But for our case, we are not going to be concerned too much about the Helmholtz free energy. We'll be concerned mainly with the Gibbs free energy, and even more so with the formation enthalpy, and to a smaller extent with the configurational entropy. So this is a materials informatics course, and so what that means is not only is the machine learning important, the materials the fundamentals of material science is also very important. Now, fundamental of material science, obviously there are many courses about it, but what our intention is, we should provide just enough foundational knowledge so that even people who are coming from a non-materials background can use this and put them into action when addressing the materials informatics problems. So that's why we started looking at the thermodynamics part. Over the next few lectures, we will first develop a few more basic concepts related to materials because those concepts will be very important in determining what type of features to use, how you calculate those features, and so on. So that is basically what we'll be doing as we move along in this course.